let's talk about the fundamental theorem of Galois theory. So we start with the Galois extension, let K over F be a finite Galois extension. And we let the automorphism group, let G denote the automorphism group K over F. Okay, so we have two sorts of objects that are related by this fundamental theorem. They are, on the one hand, subfields of K. So let's call this F for field. Script F is the set of all E, where E is a subfield of K which contains F. So E is basically a subfield of K containing F, and this is sometimes called the set of all intermediate fields of this extension. Okay, so K and F themselves are included in script F. So K, E is something that sits between K and F. So that's on the one hand. So the such objects are in script F, and in script G, so we will put so script G is the other kind of object which is now subgroups. So this is the set of all H such that H is a subgroup of the group G, okay, of all automorphisms. Okay, and one has maps between these two sets. So from script F to script G, so given an intermediate field E, one associates the set of all automorphisms of K which are identity on E. Okay, so observe this is just a set of all sigma, which is you can say it's all sigma and G. This G is automorphisms of K which are identity on F, but this is something extra is required of sigma. Sigma restricted to E should also be identity on E. Okay, so sigma should also fix every element of E, not just every element of F. So that's one. And the map in the other direction from G to script F is the following. Given any subgroup H, you look at its fixed field KH, which is just the set of all elements of K such that sigma of A equals A for all sigma in H. Okay, and as we have seen, this is a subfield. This subfield contains F definitely, because the sigmas that we are looking at, the H that we are looking at is a sub of G. Right, H is contained in G, and G is all those automorphisms of K which are definitely identity on F. Okay, so sigma will definitely fix F in this case. Okay, so these are maps in both directions, and here are some simple properties, the obvious properties. Are the following, that these maps are inclusion reversing. In other words, if I have two fields E1, E2, such that E1 is contained in E2, and both contain F and are contained in K, then the fixed field, the automorphisms, so the group that you associate to E1 versus the group that you associate to E2. Okay, since E1 is smaller than E2, the group associated to E2 will be contained in the group associated to E1. Okay, and this just follows from definition, because if an element sigma fixes everything in E2, it necessarily fixes everything in E1. Okay, so that's one direction, and the other direction is so maybe we should call this A and B. So this property 1A, and B is if I have two subgroups H1 and H2, okay, they're both subgroups of G, then the fixed fields are also have the opposite inclusion. Okay, again for just reasons of definition, H2 has more elements, so elements of K which are fixed by every element of H2, okay, will certainly fix, those elements will certainly be fixed by every element of H1. Okay, so these are both obvious properties. Property 2 here is what happens if you compose these maps. So if I take F, first go to G and then come back to F. Okay, so what does this mean? I start with the intermediate field E, I look at the subgroup H, which is all automorphisms of K which are identity on E. Then I come back, I take the fixed field of H. Okay, and the question is, what's the relationship between E and KH in general? So observe that the following holds, that KH certainly contains E. Okay, again definition, basically because elements of H already fix every element of E, right? So the fixed field has to contain E. Okay, so this is one statement. This is again 2A. B is for the opposite. You start with G, go to F, and you go back. In other words, you start with a subgroup, you form its fixed field, then you look at the automorphisms of K which fix this fixed field. Okay, then what's the relationship between that and the original subgroup H? So the left hand side here is all automorphisms of K which fix every element of KH. Definitely every element of H fixes every element of KH by definition. Okay, so again you have this, trivially you have this inclusion. Okay, so these are the various facts which are more or less obvious from definition, that these two maps F and G are inclusion reversing. Okay, so if the inclusion here goes one way, there it is the other way around, E1 sub of E2, but here it is contained. And what happens when you compose the maps? The final answer after composing the two is always bigger than the original. Okay, so these are the simple properties, and the fundamental theorem of Galois theory says really that these two maps are inverses of each other. Okay, so here's the theorem which we call the fundamental theorem of Galois theory. Which is that K over F be a finite Galois extension with Galois group G. So this group of automorphisms is called the Galois group. Then the following hold, the maps, in some sense that's really the only main content, the maps F to G, E going to aught KE, and G to F these two maps are inverses of each other. Okay, so therefore they are both bijections because they are both they have inverses, therefore, and are hence bijections. So these set up these maps give you a bijective correspondence between the set of intermediate subfields and the set of subgroups. Okay. Okay, let's prove this. Most of the work required to prove it we have already done by way of the various intermediate propositions that we have proved so far. So here's the, let's prove one direction first. Let's show that F followed by G, so we said from F to G and back, KE, then let's go back to KH. So claim is that this fixed field KH is exactly the field E. Okay, so that's one part of the theorem, because it establishes that when you compose in this order, then you get the identity on F. Okay, so let's just draw the extension tower KEF. Okay, and what's given? You're given that K over F is a Galois extension. So this is known to be a Galois extension, or given to be Galois. Okay, now the first claim, well, in order to prove what is it that we needed to prove, that KH is E again, where H is the subgroup. So all we need to really prove is that this extension is Galois. Okay, so this is now going to be our claim. If K over F is Galois, then K over E is also Galois. Is a Galois extension. Okay, that's actually all we need to prove, because let's just complete the proof assuming this claim. So once this claim is established, what does this tell you? Well, it says that recall what the one of our equivalent characterizations of Galois extensions was. It said if K over something is Galois, then the fixed field of ought. So then once established, this proves that KH is exactly E by our characterization of Galois extensions. So this was one of those equivalent conditions that we proved. Okay, where H is exactly ought KE. So look back on that theorem which we showed. So if you show it's Galois, then you're done. Okay. Now to prove this, we will use the other characterization of a Galois extension, which is that it's normal and separable. Okay. So if K over F is normal and separable, we just need to show that the same is true of K thought of as an extension over E. Okay. So let's do that. So K over F is normal and separable. Or if you look back on the same characterization of Galois extensions that we proved, we showed this. If it's normal and separable, then of course it means that for every element alpha of K, the minimal polynomial so let me call it F alpha now, F alpha of X with coefficients in Fx is, well, it splits into a product of distinct linear factors over K. Okay. In other words, when you think of it, i.e. when I write F alpha of X, it expands like this, X minus alpha I. 1 to D, let's say alpha i's are all elements of K, alpha I not equal to alpha j, or I not equal to j, and D is just the degree of F. Okay, so it splits completely and these roots are all distinct. So that's what separability means, and splits completely is the normality of the extension. Okay, now all we need to show is that the same is true when you think of K as an extension over E. Okay, so let's do the following. So now take the same element alpha, so take alpha that we are looking at in K, and so I want to think of K as an extension of E, so I need to now look at the minimal polynomial. So let G alpha of X belonging to E of X now be its minimal polynomial over E. Okay, meaning it is the unique smallest degree polynomial with coefficients in E that has alpha as a root. Okay. Now observe that So this is our usual sort of argument. So observe that f alpha is also in Ex. It's actually in Fx, but therefore it's certainly in Ex because E is bigger, and f alpha has alpha as a root, which implies that G alpha must divide f alpha, right? So this is a general fact. If I take the minimal polynomial of an element alpha over some field f, then I also look at its minimal polynomial over a larger field. Okay, so all this is happening inside some ambient field. Then the minimal polynomial over the over E will divide the minimal polynomial of alpha over f. Okay, exactly for this reason. So G alpha divides f alpha, but f alpha already factors into a product of distinct linear factors. Right, this is as we just said in K. Okay, and now G alpha divides f alpha means, of course, that what can G alpha look like? Well, it can only have, since it divides f alpha, it has to be a product of some of these factors. So G alpha is therefore a product x minus alpha I, where I belongs to some subset, let's call it S, of 1 to D. Okay, so it has to run over some smaller subset of 1 to D possibly, but whatever it is, G alpha of x again splits into distinct linear factors. This is still a product of distinct linear factors over K. In other words, G alpha is also it's a separable polynomial which splits over K. Okay. So that's exactly what we need to show. This implies by K over E is again normal and separable, since this holds for all alpha in K, i.e. it's Galois. Okay, so notice how we sort of used all the various characterizations of Galoisness here to prove that f and g are, the maps between f and g are inverses of each other. We need, we use this characterization of a Galois extension, but to show that when K over F is Galois, then K over E is Galois, it's actually more convenient to use the other definition in terms of normality and separability. Okay, good. So that establishes that one of the two compositions is the identity. So now what's the other thing that's left? We claim next. Okay, we'll show next. That the other composition is also identity. You take G, then go to F, which means I take a subgroup H, I form its fixed field, then I come back and take the set of automorphisms of K which fix KH. Okay, so then claim is that automorphisms of K over KH is exactly H. Okay, but recall this is exactly what we proved as one of the corollaries of Artin's theorem. Okay, so proof, recall, we have already done this. Okay, in fact, what was the thing we said? We said if I have so more generally we made the following statement. We said if gamma is a finite subgroup of the automorphism group, then we showed the following, that K over K gamma is Galois. It's a Galois extension with the Galois group, or K over K gamma equal to gamma. Right? This is one of the propositions we show. So now just use this proposition, just apply it to H, that's all. So take gamma equals H, and what it shows exactly is that if I take automorphisms of K over KH, then that's exactly the group H that we started. Okay, so this is done. So that proves the second half of the Galois correspondence, or the fundamental theorem of Galois theory. So that finishes the proof. Okay. So I just want to make one last remark before we end this discussion, which is that so on the one hand I have these extension fields K, E, F, and on the other hand I have the group G, which is not KF, and well, I have various subgroups H, and it's sort of useful from a symmetry perspective to put an identity there. Okay, so sort of so that it looks the same. And now observe something more. The Galois correspondence. So what does the Galois correspondence say? To each H, if I associate the field E, which is the fixed field of H, KH, then that's the bijection, right? That's the correspondence from groups to subfields. And now again we have a map in the other direction also. But this correspondence has the following very nice property. The dimensions have a nice property, which is if I look at the degree of this extension from K to KE, okay, so if H and E correspond to each other, then the degree of this extension KE is just the cardinality of H. Okay, so recall, so this is also Artin's theorem if you wish. KH, degree of the extension, is exactly the cardinality of H. Okay, and I mean, just for symmetry again, think of the cardinality of H as just being H by 1, so it's the cardinality of H by the cardinality of the identity. Okay, so what does that say? Well, that's like the cardinality of H divided by the cardinality of E, okay, or the index of the identity in the subgroup H. Okay, so that's one. Further, what about the other guy? So if I look for this and this, for instance, so observe there is just multiplicativity here of degrees. So this is one observation to make about the cardinalities of the subgroup and the degree of the extension. Now observe that KF similarly is therefore the cardinality of the group G. Okay, and if you divide this one equation by the other, that's just going to give you Kf by Ke, right? So this is my E in my figure. So Kf by Ke, because degrees of extension, so when you have a tower, the degrees just multiply. So this is just the degree of the extension EF, and so that's just the cardinality of G over the cardinality of H. Okay, which we could also write as the index of the subgroup H in the subgroup G. Okay, so you should think of, there's also symmetry in the other direction. So this index of H in G, or the quotient of their cardinalities, is the same as the degree of the extension E over F. Okay, so we will talk about sort of the second part of the Galois correspondence, which sort of asks or answers the question as to when this brown extension E over F is Galois.